Hi again. We will now solve a third example of drawing internal force diagrams for beams. So in this example we have as you can see, a beam with overhang pinned at point A and also supported on a roller at point D. There is a 4 kilonewton meters moment at point B and an 8 kilonewton force at point C, and also a uniformly distributed load running all along the beam, which has a load intensity of 4 kilonewtons per meter. So it runs from A to E. Some dimensions: 3 meters from A to B, 0.5 meters from B to C, 1.5 meters from C to D, and 2 meters from D to E. So what we have to do is to draw the internal force diagrams for this beam. Well, of course, we have to start by calculating the reaction forces. And for this purpose, we will draw the free body diagram of the entire beam. So this is the beam with a uniformly distributed load being applied all along the beam, and the concentrated force at C, as well as the concentrated moment at B. So these are the external forces acting on the beam. Then at A, we have removed the pin, so we now have a horizontal reaction AX and a vertical reaction AY. And at D, we have removed the roller, so we have a vertical reaction DY. Sum of the forces along X indicates that the horizontal reaction force at X is equal to 0. That means, if we look carefully at the beam, that there are no force components along the beam that are horizontal along the beam. So therefore, there is no axial force in the beam, and hence we will not have an axial force diagram. All the axial force is 0. Now, secondly, we can sum the moments at D equals 0 in order to eliminate the unknown at D, dy. So therefore, we can solve here for the reaction force at A, the vertical reaction force at A, Ay, which is equal to 10 kilonewtons, positive 10 kilonewtons, so going upwards. Similarly, we can sum the moments at point A, at the location of the pin, equals 0. This will eliminate the reaction forces at A from the equation and will help us calculate the vertical reaction force at D, at the roller location at D. So therefore, if we carry out these calculations, dy will be equal to positive 26 kilonewtons going upwards. As always, you must do a check at this point by summing the forces on the vertical direction to ensure that indeed your reaction forces are correct. So therefore, all the subsequent calculations will be based on correct values for the reaction forces. And these are indeed correct for this example at this point. So now in the next step, we will draw again the free body diagram of the beam with the uniformly distributed load acting on it, the concentrated load force acting on it as well, and of course the moment. The uniformly distributed load acts all along the beam. And then we have the external reaction forces at point A, which was a pin, and then at point D, which was a roller. Some dimensions. And then, similar to example 2, we will have to see what is happening to the left and right of the moment, of the concentrated moment that is applied at point B. We will need to see what is the effect of this concentrated moment on the internal force diagrams. So for this reason, firstly, we will cut the beam just to the left of point B, and then we will draw the resulting free body diagram, either the left hand side or the right hand side. So let's choose the left hand side of the free body diagram, which is a little simpler, fewer forces acting on it. So this would be part AB of the beam cut to the left of B with a uniformly distributed force acting on it from A to B. The reaction force is at A, and the internal forces, shear force and bending moment at B. We're not going to show the axial force anymore because we've established that there is no axial force in the beam because all the forces components acting on the beam are perpendicular to the beam. Some of the forces then on the vertical direction will give us the shear force at B on the left hand side of B equals to -2 kilonewtons, so going upwards on the left hand side of the free body diagram. And some of the moments at point B at the cut location will conclude that the moment at B to the left of B is equal to 12 kilonewton meters, positive number. So therefore the moment would be rotating counterclockwise on the left hand side of the free body diagram. Now at the second stage we will cut the beam just to the right of B. So it's similar as before, but we'll go one little step to the right until we pass B. So that will be cut 2. Draw the resulting free body diagram, which will be similar to the one that we drew before, except that now we will also capture the concentrated moment acting at B, right? Because we have cut to the right of B. So this is the moment at B, reaction force at A, and of course the internal forces, shear force and bending moment with their positive directions as usual. Some of the forces again on the vertical direction along Y equals to 0 will solve for the shear force to the right of B, and this will be equal again also to -2 kilonewtons. So going upwards on the left hand side of the free body diagram, which means, as we can see, that a concentrated moment on the beam does not affect the value of the shear force. The shear force stays the same, -2 kilonewtons to both the left of point B and to the right of point B. Now we also have to sum the moments at the cut location at B equals 0. So therefore this would solve us for the moment at B on the right hand side to the right of B, which will be equal to 16 kilonewton meters positively. And now if you can compare these two moments at B to the left of B and to the right of B, you will see that again that the difference between these two moments is equal exactly to the magnitude of the concentrated moment that is applied at B. Now all we have left is to draw the shear force and bending moment diagrams for this beam. So this will be here the shear force diagram having units of kilonewtons, positive shear and negative shear force, and the bending moment diagram in kilonewton meters. Positive moment meaning beam is sagging, negative moment means beam is hogging. So the shear force at A is plus 10, then it goes down by a slope of 4 kilonewtons per meter to B and then to C. So the shear force value at B is negative 2, shear force value at C is negative 4. Then it jumps downwards by the magnitude of the concentrated force of 8 kilonewtons at C to negative 12, follows through with a negative slope of 4 kilonewton meters again to negative 18, jumps upwards by the magnitude of the reaction force at D, so by 26 kilonewtons to plus 8 kilonewtons, and then with the same slope of 4 kilonewton meters, it goes down to 0. So again, the slope of the shear force is equal to the negative of the distributed load, and the jumps in the shear force at A and then at C and then at D equal to the magnitudes of the concentrated forces. So all these inclined lines have the same slope of 4 kilonewton per meter, so they're all parallel to each other. Now, with regard to the bending moment diagram, there's a pin at point A and a free end at E, so therefore the bending moment is 0 at the ends of the beam. Also, the shear force becomes 0 at a point here, let's call it F, a distance x from point A. And we can quickly calculate distance x by using similar triangles in the shear force diagram. And therefore x will be equal to 2.5 meters. Nice value, 2.5 meters from A to F. So now we can start constructing the bending moment diagram. We can calculate the change in moment from A to F, which is equal to the area under the shear force diagram between A and F. And then we can start drawing the bending moment diagram. Now the shear force varies linearly, so the bending moment will be a parabola, and it starts with a positive value, so the slope at the beginning at point A will be positive. The value of F of the bending moment is 12.5 kilonewton meters, so this would be the shape of the bending moment diagram with the positive slope shown in green at A, and then the positive slope decreases to 0 at F because the shear force at F is 0. Now we keep on calculating the moment, the bending moment, by determining the change in the bending moment from F to B. Again, this is equal to the area under the shear force diagram between F and B. So therefore the moment at B will be equal to 12 kilonewton meters. So slightly smaller. So the slope at F of the bending moment diagram is 0, and then the shear force becomes negative, so the slope of the bending moment diagram will slowly become negative. So again, 0 at F and slightly negative slope at B, where the value again is 12 kilonewton meters. Then at B, to the right of B, we have a jump in the bending moment diagram due to the application of the concentrated moment of 4 kilonewton meters. So the moment to the right of B becomes 16 kilonewton meters. And then we need to calculate the change in moment from B to C. Again, equals to the area under the shear force diagram. So that is the area of the trapezoid between B and C. That would result in a bending moment of 14.5 kilonewton meters at point C. And of course, as the shear force decreases linearly into the negative range, then the slope of the bending moment diagram will also decrease, and the bending moment diagram will still be a parabola. Now, to the right of C, we have a sudden change in the shear force. It drops from -4 to -12, so the slope of the bending moment diagram will also suddenly change at point C, will become suddenly more negative to the right of C than to the left of C. So we will expect a kink in the bending moment diagram at C. Now the change in moment from C to D results in a value of the bending moment at D equal to -8 kilonewton meters. So with what we said before, here's the kink at C, and then the negative value of -8 kilonewton meters, and the slope here is pronouncedly negative because of the magnitude of the shear force of -18 on the left hand side of point D. Now as we go to the right of point D, the shear force jumps from -18 to +8, so the slope of the bending moment diagram will also jump from a steep negative to a less steep positive value, and then the bending moment diagram will end up at 0 with a 0 slope, so tangent to the horizontal, because the shear force at point E is 0, so the slope will also be 0, the slope of the bending moment diagram. Of course, we need to do a check at the end to make sure that everything is correct. So if we calculate the change in moment from D to E and calculate the moment at E, this must result as being equals to 0, and this is what we got. So hence our values are correct. The maximum bending moment for this question was, of course, at point B, to the right of point B, and that magnitude is 16 kilonewton meters. And again, please note the kinks in the bending moment diagram at points C and D, and these are happening due to the sudden change in the shear force magnitudes to the left and right of points C and D. So that's why you have that kink, because of the sudden change in the slope. So thank you very much for watching this lecture, and I will see you again at the next one.